we know that the battery, right? We replace the battery, the car doesn't start. We know that the battery, it can't be the battery. So then we reject the hypothesis that it was the battery, and then we go on to something else. So most people know cars run on gas. Not all cars, but most cars. And so it could be that you ran out of gas. So you would ask a question, and then make a prediction. Well, if I put gas in the car, then the car would start. If my hypothesis is that the car doesn't have any gas. And so you put gas in it, and let's say then the car starts. So you would accept or support your hypothesis that the car wasn't running because it had no gas. Does that make sense? So that's basically the scientific method, and you do it all the time. Like if you came home and turned on your light switch and there was no light, then you would start using the scientific method to figure out what's wrong with it. Now, here's the trick with this, and this is done a lot in medicine too. A lot of times you just want to fix the problem and you don't really want to understand what went wrong. So let's say that someone has heart disease. And so instead of, trying to figure out if it's genetic or if it's their diet or what it is, you could just prescribe them medication that would, thin their blood and maybe lower their cholesterol level or whatever, without really understanding the root of the problem. And that's not really the scientific method, because the point of the scientific method is to figure out what the root problem is. And so this is kind of where like holistic osteopathic medicine diverges from allopathic medicine. So let's go back to the car. So let's say that the car died and you switched the battery and you also put gas in it at the same time, and the car started. Would that tell you what was wrong with the car?
No, not precisely.
No. You fixed the car, right? But you don't know what was wrong with it because you didn't have one variable changed at a time. And so that's a really important thing in the scientific method, is that in science we really can only change one thing at a time in order to see if that's the problem. And if it isn't, then we go on to the next. And so you will have multiple alternative hypotheses. Your book used an example of a flashlight. So basically you could define a problem. The flashlight's not working. Why doesn't the flashlight work? And if you don't understand how a flashlight works, you can't even begin to continue the scientific method. So you have to have some a priori, some beforehand knowledge of how something works in order to use the scientific method. Like if you had no idea how a car worked, you wouldn't even know to change the battery. So that's out. And then you're going to form a hypothesis. It's an educated guess because you have to know something about it in order to make the guess. And then you test it, right? So we replace the batteries, and then you draw a conclusion. So the flashlight works. Okay, it's the batteries. Your hypothesis is supported. It doesn't work. Your hypothesis is rejected, and you go back, and then maybe it's the bulb. So then you replace the bulb, and then that works. So then that hypothesis is supported. So does that make sense?
Yeah.
All right. So now you can make a lot of mistakes in the scientific method by making assumptions that of things that really aren't connected, but a lot of times people do this anyway. And there's lots of mistakes that are made in science this way. So a good example of this is in Phoenix, and I think I talked about this already, the consumption of ice cream increases dramatically in the summer, and so does drownings. So does eating ice cream make you drown? No. So that would be a false sense of logic of using the scientific method. And I think we talked about, 98% of convicted felons had bread within 24 hours of committing their crimes. Well, does that mean bread makes you a criminal? Eating bread? Yeah. So you have to be careful when you're doing the scientific method. Make sure that you use controls. Controls are really important, and I stress those. This helps you troubleshoot. So basically, a control is the condition when all the variables are held constant, right? So only one thing is functioning. One variable is used. So we do the batteries, right? First. And if that doesn't work, then we change another thing. So we change the bulb. And then we go to the next. Maybe it's the wiring. Flashlights aren't really that complicated. But you think of this as a person, that's sick. And so there's a lot of things that you would have to go through to figure out exactly what's the underlying cause of it. And then this is important too, positive controls. So let's go back to the flashlight, right? Let's say that you came home and all the power's out, and you have a flashlight in the drawer, and you open the drawer and you turn on the flashlight and nothing happens. So can you guys hear me still?
Yeah.
Okay. So, and nothing happens. So you would start using the scientific method. So give me an example of how you might go about with the scientific method with this flashlight that doesn't work.
The batteries are dead.
Okay, so how would you test if the batteries were dead? Okay, so let's say that you did that, and it still didn't turn on. And so the question you should ask yourself is, how do you know that those batteries that you just replaced in that flashlight work?
Maybe try a second pair.
So you would need a flashlight that that works in order to make sure what you're replacing works as well, right? Does that make sense? And so that's a positive control. A positive control is using something that works to make sure that the parts that you're changing, that you're testing, are functional in that broken flashlight. So we have negative controls and positive controls. And a positive control in this example would be a working flashlight. We have variables. So variables are things that we change, like the batteries and the light bulbs and the wires and all this other stuff, right? So the same thing we're talking about here, these variables. And then, a lot of times, and you guys probably are pretty familiar with this one because of all this vaccine development, but you got to make sure that there's no bad reactions in, if you're making a new vaccine and doing a novel way of doing it and trying to get it to the market in record time. You have to test it on big groups. And this is why drugs are really expensive, because you can't just test it on 1 or 2 people. You have to get a good range of the population. So you have to get Asians that are in a certain age group, or that maybe male or maybe female. And then you have to get, Caucasian and Hispanics and all this other groups. And you have to get, all these different age groups, because everybody could be different. Some people have mutations in a gene. One I can think of an example is that 10% of Asians have a mutation in a gene called Cytochrome P450 A1A, which I know that's a mouthful, but there's a lot. These are genes that are involved in breaking down things in the liver. So anytime you take a drug, it goes through your liver first. And this enzyme breaks down certain medications like, let's say, non-steroidal anti-inflammatory drugs like Advil. Right? So this some people might not be able to break this down into a functional drug. And so it doesn't matter how much Advil they take, it's not going to cure their pain or headache because they don't have this enzyme to convert this into a functional drug. And they're 10% of Asian population, this is broken, so this doesn't function, so they don't get pain relief from Advil, so they have to take something else. And you probably can think of examples of this that might be like, maybe you know some friends that are taking antidepressants, and maybe one antidepressant works on one person and another one works on another person, and so on and so forth. So you have to do these tests on big groups, and then obviously one group, like if you're talking about the COVID vaccine, one group would get the vaccine, and the control group would get the placebo. And so the single factor here that we're varying is, well, you get the COVID vaccine, or you don't, and then the control group, they don't get anything, just like sugar water or just plain distilled water. Does that make sense? Do you guys understand control, variable, and experimental and control groups?
Yeah.
Okay. If you have any questions, let me know. All right. So just remember, there's limitations to the scientific method. We can't answer questions that we can't test. So just imagine if you lived in the 1700s and Martians were sending radio signals and television signals from Mars to Earth. Would you be able to detect them?
No.
Yeah, because there was no such thing as radio or television back then. So we wouldn't really know, and so we couldn't say, oh, well, there's no Martians because we're not getting any signals. Well, maybe we just don't have the technology to be able to detect that. And so, you've probably seen like ghost hunters and stuff on TV, and they run around with these scientific instruments trying to measure things, like electromagnetism, yes. And so a lot of times they'll have these like UV meters, and they'll be like here, and they go off like crazy. I went on a ghost tour in Jerome with my wife and kid, and they would take us to certain places, and then this needle would like jump over here, and all these lights would come on, and they'd be like, "Oh, there's ghosts." And me being a scientist, I'm like looking, and I noticed that we're standing right under a transformer on an electric pole, which is causing this electromagnetism from the electric wires to make this needle move. But I didn't want to ruin it for all the other people that we were there, so I kind of played along. But that's a good example of, cause and effect. It's explainable by not supernatural. But, there are other things that we don't know, right? Like maybe God lives in the 14th dimension. Well, we don't have any way to detect the 14th dimension at this point in time. Maybe 100 million years from now we can, and we'll have different equipment and be able to do that. But right now, I can't. I mean, or maybe I could just say there's a green goblin that hides in my closet and messes with me that lives in the 14th dimension. Well, there's no way to test this, right? Currently. So since I can't test it, then it's not really something that's the scientific method or science can address. So just to be clear, we have to be able to observe and measure things, and those have to be verifiable and repeatable. That's why scientists publish into these journals, because it's scrutinized by other scientists to make sure that they can replicate those experiments. A great example of this, and you guys, if you want, you can look at it in the news. Um, I don't want to mess with this thing because I don't want it to stop recording. But if you look it up, there was a South Korean scientist who claimed. So a lot of people will bank their umbilical cord stem cells in case their kids get sick, and then they can use the stem cells to save their kids. So this scientist in South Korea said that he figured out a way to turn any cell into an embryonic stem cell. So, for example, you wouldn't need to bank your kid's cord blood anymore because you could just take a skin cell that was good. Let's say they got liver cancer. So or leukemia. You could take a skin cell, convert that into an embryonic stem cell, and then use that to replace defective DNA in, say, the bone marrow that would cause leukemia. And so, like, South Korean Air held him as a national hero and gave him flights, all over the world for free and all this other stuff. And they gave him $1 million speaking deals. And it turns out nobody could ever replicate that. And in the end, he finally admitted that he wasn't telling the truth, that it was all a lie. And so he was, I haven't really followed up on the story, but he was, ostracized by science and cast out as a disgrace on his country and all this other stuff. So that's why when we do these things, it has to be verifiable and repeatable so that we can be sure that the science is valid. All right, so this is that internet assignment for the cricket, but this doesn't work anymore because of the flash issue. So I'll find an alternative assignment and I'll put it on Canvas so that you guys can do something. I've been trying to find a scientific method thing that doesn't use Flash, but it turns out most of these little interactive exercises use Flash. So I'm kind of bummed that Adobe did that, but it is what it is. So I'll find another assignment for you guys to do for the 10 points extra credit on your first exam. All right, that's the end of chapter 1. So you guys have any questions about that? Anything? Okay, so now that we've finished the lecture, what you guys should go back and do is, take some notes off of the videos. And once you do that, go through the crosswords. And you don't have to do the crosswords, but you need to know the definitions of all of those words, like genome and, sessile and modal and all the stuff we talked about to classify things. You can make flashcards if you want. There's lots of other things on the internet that will help you memorize things like, flashcards or crosswords. But make sure you know those definitions. Once you get the crosswords down and you know the definitions, then go on to the study guides and make sure that you guys can answer the questions on the study guides. Once you feel comfortable with answering the questions on the study guide and knowing the definitions from the crosswords, then it's going to be time for you to take your quiz. So the first quiz, quiz number 1, it's 10 questions, multiple choice. They're each worth 1 point towards your grade. And the first quiz also uses Lockdown Browser. So this is a chance for you to test your Lockdown Browser capabilities to make sure that that works, because I'd hate for you to get in the middle of a test or start a test. And I know students procrastinate. So most of you are probably going to take the test 2 or 3 hours before witching hour when it's due. And I'd hate for it to say, oh, you have a Chromebook, so you can't take the test, because it makes it hard on everyone, including me, to try to solve that issue. So I want to make sure that everybody's Lockdown Browser works first, and that's why the first quiz has a Lockdown Browser. All right, so And the quiz questions are very similar to the test questions. In fact, some of the quiz questions will be identical to the exam questions. So, and like I said in the intro video, if you take it once and you get a 10 out of 10, you should still take it all 3 times because there's a big bank of questions, and chances are you're going to see test questions pop up in those quizzes. And the more questions you see, the more practice you'll have and the better you'll do on the exam. All right, so I'm going to close. Actually, I'm just going to open. I think this is your class. Yeah, okay.
And the quiz is due to
24th.
I don't have the dates in front of me, but it's in the syllabus and it's on Canvas. So just take a look at that, and it'll tell you exactly when they're due. I wouldn't do them all at the end. I mean, it's kind of like my example in the intro video. So if I were to give you a piece of sheet music and tell you to learn how to play this piano piece in a month, and you're going to play in front of, I don't know, someone super famous, or maybe at the Oscars or something, would you wait till the night before to try to play the piece?
Got it.
So I mean, a lot of people might, but you're probably going to suck at it, and it's going to make you flustered, which is going to make it worse. And that's what we call test anxiety. So it's much better to practice a little bit every day than to try to cram everything all at once. You're going to get better. You're going to feel more comfortable when you get to the test. You're not going to have test anxiety. So I really strongly recommend that, once we finish one chapter, you go ahead and do the crossword study guide and quizzes for that before you move on to the next chapter. But with me saying that, I know there's lots of students that are going to wait till the last couple days and try to cram it all in. And those students aren't going to do as well as students that are, keeping up with the material as we go along. It's not physically possible because your neurons in your brain make connections by repetitive behavior, just like memorizing someone's phone number or something. So you say it over and over and over and over and over again, or you make up something that you already remembered to try to remember that, right? Kind of like the King Philip came over for good spaghetti. And that's how we make connections, and that's how we make memory. So you're not going to remember this stuff if you try to cram it in. You might remember it for a day, but then you're going to forget it, and then you're at a disadvantage because when you go to micro or anatomy, they cover all of the material in 181 in the first week or two, and so you're gonna start off those classes already behind because you're not going to remember anything from this class. So that's just my recommendation. You guys do what you want.
Since the first quiz is recorded, is it okay to write down the questions as we do the quiz for like a study guide?
Yeah, I don't care. You can print them out. Like every quiz that there's an option to lock it out. You can print the quizzes out.
Okay.
Yeah. I mean, you don't have to write them down. You can just print them.
Okay.
You can screenshot them, take pictures. I don't care. Yeah.
Right, so quizzes you can use notes. And everything.
All the quizzes you can use your notes, but remember when you take the test, you won't be able to do that. So, I would try to do my best to do the quizzes without notes because that's more of a real test situation, and 60% of your grade comes from tests. So that's a big part of your grade. The quizzes are, each quiz is 1% of your grade. That means every question is 0.1% of your grade. So you could blow a quiz and it wouldn't be a big deal. But if you blow a test, that's a big deal.
Okay.
But you can use your notes. I don't care. It's just you won't be able to do that on the test. So make sure you can answer the questions without notes. All right. Any other questions? All right. So this is chapter 2. Hang on a second. I gotta move this up. I can't see that. Okay, so this is chapter 2. And chapter 2 just has to do with chemistry. I was watching The Chase. I don't know if you guys have seen this show, but it's a new game show. It's kind of a spinoff of Jeopardy, and it has those champions like Ken Jennings and things like that. And one of the questions they had was, what is the basic science that other scientists are built upon? And the possible answers was physics and biology and chemistry. And I was kind of playing along, and my wife is like, "Oh, it's biology." I was like, "No, it's not. It's chemistry, because you need to know chemistry to understand biology, and you need to know chemistry to understand physics." And this was the correct answer. So chemistry is a super important subject for anyone that's going into biology or physics or engineering or anything like that. It's the basis of everything. All matter is made up of atoms that have to do with chemistry. So everything that you can touch and feel chemistry has its hand in. So organisms are made up of matter. If we're going to define matter, we would say matter is something that takes up space and has mass. That's a real technical definition, but really anything you can touch or feel, right, is matter. And there are some things that you can't, detect with your senses that are also matter. And there's a periodic table of elements, and you can use that periodic table for the test. This isn't a chemistry class, but you have to understand chemistry in order to understand biology. So we don't look at all the elements. I'll just draw like a pseudo periodic table. So there's over 100 elements in here. We're really only going to study a few that are in the upper right hand corner and the upper left hand corner, because those are the ones that are important for life. If you took a chemistry class, all of these other ones would be important, but there's only a few, like maybe iron. Living things don't need mercury, which is Hg. So, or any of these radioactive ones down here. So there's not a lot of chemicals that you need to know here. What you do need to be able to do is predict how these things react with each other. And so element is something that can't be broken down by chemical reactions. This is what a lot of people think of as atoms, right? And so there's different elements, like we have hydrogen and helium. Most people know what that is. And oxygen. So those are examples of elements, right? And we can't break them down and still have them be the same thing. It's kind of like a Lego fire truck. If you take it apart, it's no longer a Lego fire truck. So we can't break this down by chemical reactions. There are large colliders that will smash these things and break them apart. And that's how scientists figure out what the parts are that make them up. But for this class, we're not going to do that. That's more of like a physics thing. 92 of these are naturally occurring elements. They're man-made elements. A lot of them are named after famous scientists like Einsteinium and that sort of stuff. Those aren't naturally occurring. Each element has a unique symbol, and usually that's the first couple letters of the name. But sometimes it's weird. Sometimes it's from Latin or German. Like gold is from German, and its symbol is AU, right? So it's not English. So this has really nothing related to that. Those are the ones that are tricky for students that haven't had chemistry before, because you're going to have to memorize things like sodium, for example. This is from Latin, and so the symbol is Na. And that's not really intuitive. Oxygen, on the other hand, its symbol is O, so that's easy. You know, if you your English language. Hydrogen is H, helium is He. So these are really pretty straightforward. Sodium is funky, like sulfur is pretty easy. It's F, S. Carbon is C. And so it's just a few of these weird ones that you're going to have to memorize. Any questions about elements?
No.
Okay.
No.
So, we can combine these elements, and when we combine them, it becomes a compound. You guys are pretty familiar with this. So I would bet you everyone in the class knows the chemical formula for salt. Any idea?
NaCl.
Yeah.
NaCl.
So Na is sodium, like we just talked about, and Cl is chlorine. So sodium is a metal. You can buy this on eBay if you want. It's very reactive. It's explosive in water. And so I'm not going to take the time to do this, but you guys go to YouTube, you know, and take a look. Just type in sodium reacting with water, and you'll see, you know, there are people that have bought this big chunks of sodium metal off of eBay or wherever, and then they've thrown it in a pond, and it explodes and catches on fire. So it's a very explosive element. And then chlorine, and I don't know if you guys know this or not, but you can also YouTube this. Chlorine, there's been a lot of chlorine spills, because this is an active component in a lot of things that we use, especially for cleaning. And so this is a deadly, very deadly gas. Okay. If you were exposed to chlorine gas, and I don't know, maybe you read about there was a person that died from this because they mixed the wrong chemicals together when they were cleaning, and it was a restaurant, and they died from chlorine gas. So if you're exposed to this, you would die. So we have a explosive metal, and if you don't believe me, look it up, and a deadly gas, and you put them together, and what do you get? Table salt. So just by linking these two elements together, you've taken something that's explosive and deadly and made it into something that I would consider delicious. So it's an edible compound, right? And that's because it has a different shape that makes it it has a different chemical and physical properties. So I want you to keep that in mind. Then I'm going to write this out, because this is my mantra. The most important thing in biology is the shape of the molecules, right? And, you know, you guys are probably exposed to this because you're looking at that spike protein on COVID. And if that spike protein changes, then that vaccine is not going to work anymore. So this is really critical. You know, if you design a drug to, say, block pain, then it needs to fit in that pain receptor. And if it doesn't have the right shape, It's not going to fit and it's not going to function right. So this is by far the most important thing in biology. And maintaining the shape of your molecules and your proteins is extremely critical. This is why you would die if you got a fever, because your molecules would change their shape and they wouldn't work anymore. So the molecules that carry oxygen, like hemoglobin, that's a protein, you wouldn't be able to carry oxygen to your cells anymore if you had let's say you had 107 fever. That's not much different from, you're roughly 99 degrees, right? 98.6. We're talking Fahrenheit here. So if I raise your temperature 8 degrees, it will change the shape of your hemoglobin. You won't be able to carry oxygen. And what happens if you hold your breath? Can you guys hear me?
Yeah.
Okay, yeah, you die.
Yeah.
So small changes in shape, even caused by a few degrees difference, will cause you to not be able to function anymore. So shape is really critical. So if we're looking at all the elements, about 25 of those 92 naturally occurring elements are essential for life. I don't care that you know these big numbers, but I do care that you know the 4 most important elements. And those are carbon, oxygen, hydrogen, and nitrogen. Those make up 96% of all living things. And the rest of it is phosphorus. And you guys will see this is a really important I'm probably dating myself, and you guys probably didn't have this at all. But they used to make these things called Tinker Toys. And they were little wheels, and they had holes in them. And you'd put a stick in there, and then you could get another wheel, and you could make, these crazy designs by, adding all these sticks to it. Well, this is how atoms are, right? And you're going to learn that some atoms have 1 hole, and some atoms can have up to 4. And so if I only had 1, if there was only 1 hole in this wheel, they're made out of wood. These Tinker Toys there's a hole here. You put a stick in it, right? But can I put any other sticks in this if it only has 1 hole? And the answer is no. And let's say I had another one. So only having 1 hole, you can only make this structure. It's not very complicated. But if I have 4, then I can make really complex molecules. And you're going to learn hydrogen has 1 hole. It can make 1 bond. Like you can add 1 stick to it. And carbon has 4. And because carbon has 4, oxygen has 2, carbon has 4, hydrogen has 1, nitrogen can have 3 or 5, and we'll talk about why that is later. But it's mostly 3. And so of all these, what do you think you can make the most complex stick figures out of? And the answer would be the one with the most holes, which is carbon. So this is why carbon is really important to life and to living systems. Can you guys hear me still?
Yeah.
Awesome.
Yeah. We can.
Okay, so we're going to get into why this is, but make sure I will ask you probably on the test, what are the 4 most common elements in living systems? And you need to know this. So make sure you do. And then phosphorus. So you'll see when we get to chapter 4, this is a principal component in DNA. And we talked about DNA. All living things need DNA as their instruction book. And then sulfur. This is found in proteins. And proteins make you what you are. They make you flesh and blood. So these are the next 2 common. And then calcium. You guys know what this is for. Probably bones. And then some sea organisms use it for shells. And then potassium. And you'll learn why calcium and potassium are important, because we can use this to conduct electricity. And this is the symbol for, this is electron symbol. So moving electrons is called electricity. All right. Any questions about that? Okay. So the most abundant element in any living system, but in the human body in particular, is oxygen. It makes up 65% of you. A lot of people would say water, but remember water is H2O, and we're just talking about elements. So we're talking about this, and the answer, and this is by mass, because this is heavier than this. So I might ask you on the test, what's the most abundant element in the human body by weight or by mass? And what would you tell me? If you want to get it right, you'll say oxygen. So remember we said oxygen, carbon, hydrogen, nitrogen. Those are the 4 big ones. So make sure you know those too. All right. So the structure of the atom is important in determining the chemical and physical properties of that particular element. And each of these atoms is composed of smaller parts. Scientists know this because we smashed them together. Imagine that if you can only see something so small as like a Lego fire truck. I don't know why I'm stuck on that, but or let's say a Lego. You have a Lego fire truck and a Lego Batmobile. I'm just pulling this out of thin air, but so that's all you can see. You can't see the parts that make it up. So how would you find out what makes up, what kind of Legos are in the Lego fire truck? You'd have to take it apart. Well, we don't really know how to do that. So what scientists do is they have these big particle colliders, and they take the 2 Lego structures, the fire truck and the Batmobile, and they smash it together. And then what happens?
They come apart.
Yeah, all those pieces fly all over the place, and they leave little signatures that we can detect because they have a charge or they have a certain mass. So, you could tell that one of those big square Legos with the 8 circles on top is bigger in mass than, say, one with just one little connector. And that's how we figured out what atoms are made out of. So they've smashed them together. There's lots of stuff. If you took chemistry, you'd find out that there's many, many other subatomic particles than this. But these are the main ones, and this is really all you need to know. So neutrons, they know that they have no charge, and they know that they weigh 1.009 daltons. All right, well, because we're not in chemistry and we're not building nuclear weapons or anything like that, we can round this off. So we'll just forget that decimal. We're just going to call it a 1 dalton. And a dalton is named after a guy, like a lot of stuff in science, like Escherichia coli is named, that bacteria in your colon is named after the physician Escherichia that discovered it. And then we have protons, and protons have a positive 1 charge, and they're 1.007 daltons. So this is just a unit of mass. When you guys do the metric system, you'll figure out that they just made it all up. So it's kind of like, you guys know how they measure the mass of a diamond?
Is it the weight?
Yeah, what do we call that?
The carats?
Yeah, so you know where that came from? Because it's the equivalent of the weight of an average carrot seed. So it's just a made-up unit, right? And they could say, okay, well, what if they based it off the weight of a pea? Then maybe it wouldn't be called carrots; it'd be called peas. So don't get hung up on this dalton. It's just a name like teaspoon or tablespoon or cup. And I'll show you. We don't generally use this word anyway. We usually convert this to grams. which is another made-up unit, and you'll learn that when you do the lab on the metric system. Anyway, and then electrons, it has a -1 charge, and it's 1/2000th of a Dalton. So this is so small. For biology, we can just call this 0, right? So you're going to need to know this because this is going to help you predict things, and I'll show you why. But you need to know that neutrons are no charge, and they have a mass of 1. Protons have positive charge, and they have a mass of 1. Electrons have negative charge, and they have a mass of 0. And you can remember Daltons if you want. And you will need to know that for chemistry, but for us, we're usually dealing bigger stuff, so we're gonna convert this to gram later on. Grams. So this is helium, right? Helium is in the upper right-hand corner of the periodic table. If you look at a periodic table, you'll see that underneath helium, it has a mass number. That mass number is 4. And on the top of helium, it has what we call a atomic number, and that atomic number is 2. And we can get a lot of information from this. So this means it's 4 Daltons, which ultimately we're going to convert to grams because they're easier to work with. This is the number of protons it has. So helium has 2 protons, and its total mass is 4 Daltons. So that tells me I can figure this out, how many neutrons are in there, because what do electrons weigh? 0. And if there's 2 protons, what would that weigh? 2. But we know the weight is 4. So we take 4 minus 2, or the mass minus the number, and that gives us 2. This has to be the number of neutrons, right? Because it has to weigh 4, and the only way to get there without adding protons is adding neutrons. Now, I could add a proton to this, but then it would become another element, because every element has its own number of protons that make it unique. So hydrogen is 1, and its atomic mass is 1. So how many protons does it have? It's the same as its atomic number. It has 1. And how many, since its weight is 1 Dalton, how many neutrons does it have?
1.
If it had 1, then what would it be its mass?
2.
Right, and it's not. So how many neutrons does it have?
0.
Yeah.
0.
Now, if I wanted it to be a mass of 2, if I added a proton to it, then it would have 2 protons. By doing that, it would no longer be hydrogen, it would be helium, because the protons dictate what the element is. And let me show you that. You guys can still see this part of the screen, right?
Yeah.
Okay. So here's a typical periodic table. I know these numbers are super small, but so this is hydrogen. Its number is 1, right? If I added a proton to that, so this has 1 proton. If I have a proton to that, it becomes helium, which is over here, which is number 2, which is shown here, right? And then this is its mass. We truncate this off, so that's really 4. This one, its mass is 1. We don't. There's a reason that this is the way that it is. I don't want to confuse you guys, but it's basically there are isotopes, and they take the average weight of each isotope of each element and add it together, and then divide it by the number of percent of atoms that are found on Earth, and then they average that out. So that's how they get that number. So like carbon, it's got 6 protons and its mass is 12. So how many protons? 6. How many neutrons in carbon?
12.
No, that's its total protons plus neutrons. So how many neutrons?
6.
Yeah, 6.
6.
And to figure that out, all you got to do is take, it's not going to let me draw this, but all you got to do is take 12 and subtract it from 6, and that'll give you the number of neutrons. We could do the same thing for lithium. So lithium is 3, and its atomic mass is 7, so how many neutrons?
4.
Yeah, 7 minus 3 is 4. We could do the same thing with oxygen. Oxygen its atomic number is 8, its mass is 16. How many neutrons? Yeah, 16 minus 8 is 8. So we can do that with anything. And that's going to be really important because we need to know, in order to predict reactions, we need to know the number of protons and the number of neutrons and the number of electrons. So to make this thing electrically neutral, I'm just going to go, I'm going to close this and let's go back to this. So helium, right, it has 2 protons that are positively charged and 2 neutrons that have no charge. So the charge inside of here is +2. So if we want it to be electrically neutral, we need 2 electrons. Does that make sense? So these things spin around like they're planets, or like the moon spins around the Earth, but they spin at the speed of light. So they make this cloud, which is what this thing is showing here. Okay, so we can predict just from the periodic table, we can predict how many protons, neutrons, and electrons. So let's just practice this. So let's look at nitrogen. Okay, so nitrogen is 7, and for the test, you guys will have a periodic table, so you don't have to memorize all this. So nitrogen is its atomic number is 7, its atomic mass is 14. So let's just write it down. So nitrogen, its number is 7, its mass is 14. So let's try to figure out how many protons, neutrons, and electrons there are. Okay, let's start with protons. It's easy. It's the same as the atomic number, right? So we know it has 7. Now, if it's electrically neutral, how many electrons would it have to have?
7.
Yeah, because these are all plus, these would all be minus. And then how many neutrons does it have? 7, because 14 minus 7 gives us the number of neutrons. So you've just figured out all the subatomic particles for nitrogen. And we could, well, let's do one more. Let's do carbon. No, let's do sodium. So you guys know about sodium. So its atomic number is 11, and its mass is 23. We're just rounding up. Okay, so sodium Na, sorry, is 11, and its mass is 23. So how many protons?
11.
Awesome. How many electrons?
11.
Awesome. How many neutrons?
12.
Exactly. Does everybody understand how she got that? Awesome. So this is the sort of stuff that you're going to need to be able to do on the exam. And it's pretty straightforward. You just need to know that you need to know this, basically this table. All right. This is just neon. I just use it as an example, but we just did a bunch of other ones, so we're good. So this is just a recap. The atomic number is the number of protons in an atom, right? And every atom has a different atomic number. If we go through the periodic table, you'll see hydrogen's 1. If it wasn't 1, it wouldn't be hydrogen. If it was 2, it'd be helium. If it was 3, it'd be lithium. If it was 4, it'd be beryllium. 5 is boron. 6 is carbon, and so on. None of these have the same number, right? Because if they did, like alchemists back in the day would spend forever trying to turn gold, which is 79, into, or sorry, lead, which is 82, into gold, which is 79. And you could do that. How would you turn lead into gold?
Neutrons and protons.
Yeah, you'd have to subtract exactly 3 protons to make gold. If I only took away 2, I'd make mercury, right? If I took away 1, I'd make thallium. If I took away 1, 2, 3, 4, if I took away 4, I'd make platinum. If I took away 5, I'd make iridium, and so on and so forth. So we can change one element to another, and we could certainly change lead into gold by removing protons, but it costs a lot more money than gold is worth. So because it takes a lot of energy to strip protons off of elements. But anyway, you guys get the point, I'm sure. So the number is unique for each element, and I think you've seen that. The atomic number is written as a subscript before the symbol, and in a neutral atom, the number of what equals the number of what? So electrically neutral.
Protons equals electrons.
Yep, that's exactly right.
Protons
equals electrons. So we can always tell from the atomic number, the number of protons, the number of electrons. And then if that's a neutral atom, right, it has to be neutral of any element. And then we can use the mass number to figure out the number of neutrons. And we've already done that. Now, I talked a little bit about isotope. Iso means same. Tope means element, essentially. So an isotope, it means it's the same element, but it has a different number of neutrons, so its mass is different. A good example of this is carbon. So we go and look at carbon. I'm just going to flip back to this slide. So here's carbon. Carbon's mass is 12. Its atomic number is 6. So I'm just reminding you guys. So the standard carbon is mass of 12 and number of 6. So that means it has how many protons? 6 protons. Awesome. And electrically neutral, how many electrons? 6. And then how many neutrons? 6, because 12 minus 6 is 6. And that's how I got that. Now, if I could add a proton to this, but would it be carbon? No, it would become nitrogen, because nitrogen's 7. So I can't do that and keep it the same element, right? But if I want to change its mass and keep it the same element, I can add another neutron. So if I add a neutron, what do neutrons weigh? 1 Dalton, right? So instead of being 12, it would be 13, and instead of 6 neutrons, it would have 7 neutrons. So carbon-13 exists, and it has 7 neutrons. And you guys have probably heard of carbon-14, right? It's very commonly used to date fossils. And so how many neutrons would carbon-14 have?
8.
Yeah.
8.
Now, I'm going to go back. I just want to explain this real quick. I don't care that you know this or not, but so these things are positively charged, right? And in your life, you know that if I put two positively charged things together around something that's electrically neutral, what do they want to do? Two pluses, like two plus magnets together, what would they do? Yeah, and so what would happen if the center of the atom, the nucleus, with all the plus charges in there, pushed away from each other? Yeah, it would explode, right? It would throw off particles, protons, and neutrons. And so these neutrons, they act as like a glue to hold this stuff together. And this is called the strong force, and I'm not going to get into it. You'll learn that when you take chemistry or physics. But when we start changing the number of neutrons inside the nucleus of an atom, it starts making it unstable. So carbon-14, now that we've added 2 more neutrons in here, the nucleus is unstable, and it starts becoming what we call radioactive. And because it's unstable, it shoots out particles, or it could convert one particle into another. It's kind of a magic trick, and again, I don't want to get too deep into this, but it has fundamental roots in chemistry and physics. And so we're just talking about the various mass numbers. So we talked about carbon-12, and we're talking about carbon-14. Carbon-14 is an isotope, right? Same element of carbon. It just has a different number of neutrons. So let me just back up. So what happens here is when we get 14 of these inside the nucleus, one of these neutrons, so we've said we have 8 neutrons and 6 protons, one of these neutrons becomes a proton. So if that happens, if one of these neutrons becomes a proton, how many protons would we have?
7.
Yeah. Dang it.
7.
We have 7 protons, and then remember we had 14 neutrons, but one of them became a proton. So how many neutrons would we have?
13.
Well, its mass was 14 before, right? And so it's nitrogen 7, but it still has the same number of neutrons. So before we had 8, right? 8 neutrons. So now we would have how many since one became a proton? 7. and its atomic weight would be protons plus neutrons, which would be 14, right? So what I want to show you guys is that carbon-14 decays into completely stable 7,14 nitrogen. So carbon-14, when it gets that number of neutrons inside of it, it can change to nitrogen, and then it becomes stable again. All right, so that's an example of an isotope. And elements occur in mixtures of isotopes. So if we went and we sampled, remember we talked about carbon as one of the top 4, and if we sampled all the carbon on Earth, we would see that most of the carbon is carbon-12, and then about 1% is carbon-13, and then an extremely small portion is carbon-14. And carbon makes up sugars like you find in fructose and sucrose and glucose. So, you know, if you're drinking a soda that has high fructose corn syrup in it, or maybe it's you know, Mexican soda and it's real cane sugar, so it's sucrose. But these carbons, right? There's going to be billions of these carbons in a can of, let's say, Coke. And so a small percent of these carbon in this can of Coke is going to be carbon-14. And a small percent of the carbons will be, or a bigger percent will be 12, and then another percent would be carbon-13. So when you drink this, let's say you drank too much Coke, you would store that in your body as fat. And that means so fats are fatty acid chains, so they're carbon chains like this. And we'll learn that in chapter 5. So some of these chains would be assimilated as carbon-14, and some of these carbons in these chains would be 12, and some would be 13. Most would be 12, right? But that means you're going to have some radioactive carbon that's inside your body that you got from this can of Coke. Does that make sense?
Yeah.
Okay. So, and it's true with like the food you eat. So like you ate Doritos or, you know, a sandwich or even lettuce. It's going to pull out carbon dioxide to make, you know, the leaves of the plant. And so everything that you eat is going to be a certain percent of carbon, and that's going to become you. Like you are what you eat. So that means that through your whole life, you're assimilating carbon-14 in a specific percentage in your body. And so this is what these are the exact percentages. I don't care that you know these. You don't need to know these. What I'm trying to show you is that so if I sampled all of your carbon and your, you know, hundreds of trillions of atoms that make up you, I would find that 0.00000000001% of all those carbons that make you what you are, because you're eating, drinking, you're assimilating carbon into your body, this would be the percent that makes you. And this would be the percent of carbon-13 that makes you, and this would be the percent of carbon-12 that makes you. Now, let's say that you died. You just kill over and die. So are you taking in any more carbon?
No.
No. And what happens to this carbon-14?
Decays.
It's unstable, right? And we said it becomes
Decays.
nitrogen. So the half-life of this is about 5,400 years. That means that this percent will be 1/2 of that amount in 5,400 years. And then another 5,400 years, it would be another half of that. So it would be a 0.5%. Let's just exclude all the zeros. But this 1 would be a half. And then what's a half of a half? Is a fourth, right? And then, so if I dug you up and you were dead for 10,800 years, I would expect you to have 1/4 of this percent of carbon-14 left in your body. And that's how we can date these fossils, by measuring the amount of carbon-14 that's left. Because the other half has become nitrogen, which is a gas and floats away. Does that make sense?
Yeah.
So this slide is just going over how we do carbon dating, and we already talked about how carbon becomes nitrogen. I'm sorry, I lied. It's 5,700 years. And you don't need to know that. I'm just showing you how we can use radioactive isotopes in order to date things. And so this is the half-life, right? And that's the time for half of the carbon-14 to become nitrogen. And different elements can be isotopes and be radioactive, and we can use those for different measurements. Because here's the thing, right? If you're halving, let's say you have a brick and you half it again, and you half it again, you half it again, it's going to get so small that you're not going to be able to measure that. You can't measure it. It's too small. And the same thing happens with carbon-14, right? There's a point where the half-life is, it's been 5,700 and then another 5,700 and so on. So let's say there was, 10 half-lives. That would be 5,700 plus 5,700 and so on and so forth. So 57,000 years. That's 10 splittings of this. And if we're looking at, 570,000 years, well, that would be 100 splittings of this brick. And you can see where it would get to the point where like 5,700,000, that will be 1,000 splits, half. And so, at that point, it's so small that carbon dating isn't useful anymore, and we have to use something else, like maybe uranium, which has a half-life of, millions of years instead of thousands of years like carbon-14. All right. So this is exactly how scientists determine the dates. This is a natural log value. This is the half-life. This is the ratio of free nitrogen and bound nitrogen. You don't need to know this for the test. It's kind of just for math geeks, I guess. But anyway, so you can plug in these numbers. Let's say you found a skull. The carbon-14 compared to living samples is 0.1. Then you could plug in these numbers and figure out that this thing is 18,941 years old. Again, you don't need to know this for the test. I'm just showing you this is how we can use these isotopes, these radioactive isotopes, to date living things. You should know half-life, right? So if I say the half-life of carbon-14 is 5,700 years, how much of a brick of carbon would you expect to be left after 22,400 years? Right? Yeah, I think so. So the answer would be it would half after 5,700, right? And then it would half again, so you'd have a quarter left after 11,400 years. This would be 8. And then it would half again, another 5,700 years, which would be an 1/8. And then it would half again after the fourth 5,700 years. So you would have 1/16 the amount of carbon-14 that you would expect in a living thing. Does that make sense? You guys there?
Yeah.
I bore you to death. Okay. So, anyway, so we're about an hour and 15 minutes into this thing, and I'm going to go jump over to office hours. We'll pick up here, but you guys, you know what electrons are, so we're going to start talking about where these electrons are located and how we can use these electrons and what we've learned to predict how chemicals react on Thursday. Any questions?
No, today's lecture is pretty straightforward. Thank you, Professor.
No problem.
No,
All right,
today's lecture
I'll
is pretty
see you guys in
straightforward.
office hours, or I'll see you on Thursday.
Thank you.
All right, have a good one.